topic relatively quickly, one lecture to cover that. And yeah, that's it. That's the cutoff for the next exam, which is on Monday. Questions about any of that? No? Let it rip if you do. I can't see you, so. So if not, just remember what's been posted in terms of assignments now. You have a quiz over Chapter 9, which is due on Wednesday. And I asked you to get a start on that because it's just good, because you had some of the information you needed to address at least some of those questions since last week. But also because we have another assignment. So the class day assignment number 4 is now available. On Canvas. So this CDA, remember, has a reading assignment, and that was posted some time ago. But devil's advocate, many of you maybe have not done that reading, and it is the best way to attack this assignment, to do the background reading. Is the full Monty, I think, to get the full experience, you should do the reading. So let's say tomorrow midnight. Okay, so you have one assignment, the CDA due tomorrow, and then the quiz the day after that. Okay, that's it. Stay on top of it, folks. You don't want to mess around with metabolism. Any questions? Nothing? Really? Okay, so maybe you have some questions over the content. And so what I thought we'd start out with is a summary of all the things that we've covered so far in respiration. We've covered a lot, okay? And what I would encourage you to do for a change is just to sit and listen. I'm not saying anything new. It's all been said before. So if you're taking notes so far, then you really don't have to take notes. If you want to, do a memo recording or something, or just take a photo of the slide, that's fine. But just sit and listen. I think maybe that would be a nice segue into this lecture. So we're talking about cellular respiration, recall, which is summarized by this equation you should know very well at this point, right? You should know the equation summarizing the process of respiration, just as you should know the equation summarizing the process of photosynthesis. We'll talk about that on Wednesday. It is a process involving many chemical reactions, which we said we would break up into 4 stages for the sake of simplicity, right? And we said that, but that, of course, is the convention to break it up into the 4 stages, 3 of which we covered, right? So what have we seen so far in those 3 stages? Recall that all of those stages involve oxidation. Let's see, there's at least one oxidation reduction reaction in all of those stages, quite a few actually in the 3rd, right? And in all of those cases, the oxidizing agent is what? Everybody.
NAD.
NAD. Okay, that is super important that you know what those terms mean, oxidizing agent and reducing agent. But really, oxidizing agent is the one that comes up over and over, the one that people reference, the one that I'll be asking you both today, questions like that, and on the upcoming quiz and exam. Okay? So yes, make no mistake, the oxidizing agent in stages 1, stages 2, stages 3 is NAD. And altogether, we actually oxidize the sugar 10 times, right? 2 with glycolysis, 2 with pyruvate oxidation, and then 6 in the citric acid cycle. 2 plus 2 plus 6 is 10. Okay? So remember what NAD is. We said a lot about it, but we actually didn't say a lot as well. The D, anyone know what the D stands for in NAD? It's an acronym. Okay, so I think I heard it, but probably most of you, unless you're reading the book, which is also a good idea to really get the full scope, as usual, it is dinucleotide. NAD is dinucleotide. It's nicotinamide adenine dinucleotide. And I told you it's a monomer, right? Which is, it's 2 monomers, right? If it's a dinucleotide, that's 2 nucleotides, or 2 monomers, right? So pretty close, right? Also, know that in being the oxidizing agent for sugar, it's going to carry electrons. Right, so it really, its role is to carry electrons from these first three stages to the fourth stage, right? So it's an electron carrier. That's another way we reference it. People say electron carrier, NAD. In its reduced form is NADH. Recall that's the reduced form, and that's the form that not only carries electrons, but also carries what? Energy, right? I mean, the whole point is to take away the energy of glucose and utilize it, right? So by taking away the electrons, we take away the energy. It's stored in NADH, okay? And another term I applied was coenzyme, right? Coenzyme is another way to say it's a carrier. It carries something. So electron carrier, coenzyme, they're all terms that people use and I think are really good to know and be familiar with, okay? NAD reduced to NADH. Also in stages 1, 2, 3, recognize that we completely catabolize glucose, we completely break it down, and so by the end of the third stage, we have all the carbon dioxide produced, right? We could convert glucose into CO2, right? So you gotta remember where those things happen, right? So we said 2 CO2 are produced, pyruvate oxidation, 4 more in the citric acid cycle per glucose. So 2 plus 4 is 6. And again, remember the tabulation is important. That's something you should be nailing down. Also remember that there is a little ATP made in those stages. What stage or which ones maybe in particular? Does glycolysis make ATP?
Yes.
Of course it does. That's pyruvate oxidation.
Yeah.
Now that's the one that does not, and the citric acid cycle does. Right. So citric acid cycle and glycolysis make a little ATP. How does it happen? So I don't think I'm going to talk about that because that's your charge. We talked about it already. But be aware of 2 things. When we're talking about making ATP, you should know what it's made from. Any reaction has reactants. What reactants is it made from? It's actually different in these stages versus how it is done in stage 4. Okay, so I'm going to include it for you. The other thing to keep in mind is what is the source of energy? Remember, making ATP is energonic, requires energy to do that, and the source of energy is also distinct, and they go hand in hand, right? The reactants are slightly different in the 2 ways of making ATP, and within that you see that the source of energy is likewise different. So it makes a little ATP how, it's up to you at this point. Stage 4 we talk about today. Stage 4 is where NADH will give its electrons away and is therefore oxidized. So we'll start actually with the oxidation of NADH, which then begs the question, with what? Okay, hold that thought. We've said actually what the oxidizing agent is early last week, but we'll talk about it. We'll talk about it shortly. Make no mistake, by handing off its electrons, NADH really sets the stage for making a lot of ATP, and that's where we're in stage 4, we're making a lot of ATP. How do we do that? We're yet to see that. Okay, and again, remember, when ATP is made, to note the reactants used to make it, and also the source of energy. Okay, now questions. Questions about anything we've already covered. This is a good time if you're not sure about something. Yeah. Yeah, that's it. That's the answer. So just be careful. I think I heard the T in there. Inner membrane. Very good. We said that inner membrane of the mitochondria is what oxidizes NADH. And so you're exactly right. And good to point that out. Yeah, what else? All right, if not, just one more time, I want to make the point that most of the energy that's been harvested from glucose is now within NADH, right? Again, the orange font suggests energy, and you want to watch the flow of energy as we go through this. So what is NADH oxidized by? He was anticipating clearly where we're going. We did say the inner membrane. The inner membrane of the mitochondria is what gets the electrons. Okay? Making the inner membrane the what again? Oxidizing agent. Absolutely. Specifically, what though? So membrane, we've commented on how it's made from phospholipids, right? That's not any different from mitochondria as it is the cell membrane, right? All membrane is constructed from phospholipids, but it contains other kinds of lipids, which we've also noted. It also contains protein, right? So what exactly receives those electrons? That I can tell you now. And what is the oxidizing agent of NADH? More accurately, it's the electron transport chain. The electron transport chain. Well, that's new. We'll have to see what that is. Recall that the inner membrane of the mitochondria has significance. Right? We talked about how it's highly folded in chapter 6, right? And the thought in your mind at that time should have been, I think, what's the deal? What's the story with this membrane versus the other one? Why? So folded. I mean, you can take it a step further if you understand, things like maybe digestion, how digestion works, or how things like how pumps work, and so there's a lot of analogies you can maybe draw on. Anytime you have a surface area, like a huge surface area, it's of significance. It's of some value, right? So you got an intestine, for example, and you've got two intestines, right? I guess, large and small. Which one goes like that, and like that, and like that, and like that, and like that? The large or the small? Okay, exactly. The small goes like that, and like that, and like that. And what's the deal with that?
Surface area.
It's a surface area. Clearly, that longevity is of significance, is of biological importance. And it's a surface area, of course, for absorption, well, for digestion, as well as absorption of nutrients. Okay, so clearly, we got a surface area. Now, we've already said that that surface area contains an enzyme. And that enzyme is the enzyme that makes ATP. And you'll remember what it is? ATP synthase. Wow, very good. All right, so I think it's a good time to remember. So let's just say it again. So the enzyme ATP synthase is the enzyme that synthesizes ATP. It makes ATP. And it is found within the inner membrane of the mitochondria. It's a membrane protein. What we said was that this part is embedded in the membrane, but this part is sticking out into the matrix, right? And then that top part is sticking out a little bit into the intermembrane space. So again, the matrix, being the internal compartment of the mitochondria, the intermembrane space is the space between the two membranes, right? The inner membrane is right there. Another thing we said was that in order to make ATP here, there has to be a change of shape, right? A conformational change occurs. And that's kind of what puts together the reactants that make ATP. Okay? And then I showed you this animation, which suggested how that could happen. There is indeed a rotor in this portion of the protein that turns, and that rotation is what causes that conformational change, and then makes ATP from a series of active sites around the enzyme. Okay? So what we said was that as long as you can turn that rotor, you can make ATP, which then begs the question, where does that energy come from? Okay, so now we get to it. Now we can connect the dots and explain how that happens. So with that said, stage 4 is oxidative phosphorylation, we call it. phosphorylation. And if you're following along closely with my slides, my apologies, because I did tweak the word a little bit, wording. It's largely the same, but some tweaks, just heads up, okay? Little tweaks and maybe a little shifting of the slide. So my apologies if it's confusing. So please recognize that just like glycolysis involved a series of enzymes, right? And pyruvate oxidation a little bit, citric acid cycle, several enzymes again. So does the oxidative phosphorylation involve several proteins which are enzymes. However, these proteins are embedded within the inner membrane of the mitochondria. Okay, several membrane proteins actually in the inner membrane. Okay, so what's the deal? We already said ATP synthase is in that position. Well, well, yes, but we're also saying that these proteins, these enzymes of stage 4 are also there. All right? I think my slide did not have both of them in there, so I thought I'd put up my game there, put it all in there. It's getting crowded, right? We have the ATP synthase enzyme, but then we also have these enzymes. And just like glycolysis, how many enzymes catalyze glycolysis?
10.
It's a lot. Yeah, well, it's not that many. It's also a finite number. How many?
10.
10, right. So 10, which are in large number in our cytosol, right? Citric acid cycle catalyzed by how many enzymes? Less than 10? 8. Yeah, citric acid cycle is catalyzed by 8 enzymes, which are in large number within the mitochondrial matrix. Right? So remember that there's a multiplicity of the enzyme, not just one of each. There's so many enzyme 1, so many enzyme 2. Likewise, so many enzymes of the oxidative phosphorylation. And so what I tried to do is, to suggest several enzymes here, and then here, and then here, right? Because each of them is present in so many copies. Does that make sense? Okay. Okay, so that's where we've really now shifted, aren't we, to focus on the inner membrane, right? So we were in the matrix with the citric acid cycle. Now we're at that inner membrane. What these proteins do is perform a series of redox reactions. A series of redox reactions. I know we've seen redox before, but this is now a series. Meaning the first enzyme gets electrons, right, from NADH, okay? And then gives those electrons to who? The next enzyme. That's it. Which then gives the electron to the next enzyme, and so forth as you move down this chain. It's called a chain because you're just passing down the electrons, right? The chain is called what? Electron transport chain, we said. Right, well that makes sense. If you think of that transport as being the transport of electrons. Again, just one oxidation after the other. Okay? So your textbook has a much better figure of the electron transport chain, and this is it. Now this is a busy one. And for that reason, I went ahead and blanked out some of the figure. Okay? So let's look at it together. This is the inner membrane, right? Not labeled now that I'm seeing that. This is the inner membrane. The outer membrane is over there, so that makes this the intermembrane space. The inner membrane encloses the matrix. Okay, that's there. All right? Within that inner membrane are several proteins which constitute the electron transport chain. Okay, so there they are. The line or arrow in yellow is what? Okay, very good. The transport of electrons was what I heard. Yeah, exactly. So there it is. Okay, so here's NADH now, produced by stage 1, produced by stage 2, produced by stage 3. At last, handing its electrons to the first chain protein, right there, which then hands the electrons to the second chain protein, and the third, and the fourth, and the fifth. There it is. That's the electron transport we're talking about. Okay? Question? All right. Your textbook has another figure of the electron transport chain, and it's both simpler and also more complex than this figure, and I think we should look at it now. This next figure shows the electron transport chain in the form of an energy diagram, right? A change in free energy diagram, like so. Okay, so here you have the progress of the chain on the x-axis and energy again, delta G on the y. All right? And the first thing to recognize is, where's NADH? There it is, with its level of energy, notice, up there. And it hands its electrons to the first chain protein. Okay, there it is. Now, I said this is both simpler and more complex, right? So it's simpler in that there's no inner membrane, there's no matrix intermembrane space, and then all the arrows and all that is kind of removed. But it is more complex in that it shows more proteins. It does show more protein. The first protein to get electrons is flavoprotein. I put it in there so you know. The first protein is flavoprotein. The second protein is actually that protein. Okay, I don't want you to know it, so I'm not going to name it. And then the next protein is that protein, which it says Q, I guess? Where was that here? Oh, yeah. Yeah, okay. So what's going on here? Why are there more proteins than in here? The point is to understand that the proteins of the electron transport chain function as complexes. Remember we said that enzymes can function more efficiently in metabolic pathways through a variety of ways. One of those ways was putting them together into multi-enzyme complexes. That's what this is. These first chain proteins are both within this first complex. These three chain proteins are within a complex of protein. Okay? So we're seeing that aspect, right? So, and recognize the value, because what are the proteins doing? They're transporting electrons, right? So the electrons go from NADH to flavoprotein, from flavoprotein to FES, from FES to Q, from Q to cytochrome B, and each protein need not, look around for the next protein if it's already bound to it. Okay, in fairness, each protein could look around and relatively quickly find the next protein, because these are all in the membrane. I mean, these are all in the inner membrane. We've talked about the fluidity of membrane. So it's not hard for one protein to find another. But if you're already bound to the next protein, then you just go boom, boom, right? And then find the next one, boom, 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 right? There's an efficiency that's going to provide. Okay? So, redox, reaction, redox, 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 until we get to the end. Okay? Everyone see what this is? Okay, complexes. They're complex. The chain proteins are within complexes in the electron transport chain. The next thing to recognize is there's a change in energy involved. What is happening to energy, the energy of the electrons? Is it going up or is it going down? What does the figure show? Energy increasing or decreasing? Decreasing, yeah. Well, it was up here. It was up here with NADH. Redox, oop, we lost some. Redox, oop, we lost some more. Redox, 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 and the electrons are losing their energy, right? Absolutely, it's going energy. It's losing energy. And you know what okay, let me address this next question, then I will present an analogy. What does this say about the relative electronegativities of the chain proteins? How does the electronegativity, say, of FES compared to Plato protein? Is it more or less electronegative? Maybe less electronegative? That's why the electrons are losing energy? It's more electronegative. Remember, if you're more electronegative, what do you do with bonded electrons? You pull them closer, right? And they lose energy. You pull them closer to your nuclei, and they lose energy. So with every subsequent chain protein, there's a loss of energy because every subsequent chain protein is more electronegative than the last. Right? Or whatever atom is carrying the electron is more electronegative than the last. Does that make sense? And you got to think about your polar covalent bonds there. All right, so what I was going to say is this is like hot potato, right? This game. Okay, to be honest, I've never played hot potato and I don't know how to play. But I think the idea is the potato is hot, right? And because it's hot, you pass it to the next player, right? It's hot again, right? It's still hot. And so you keep passing. I mean, potatoes can be pretty hot, right, when they come out of the oven. And so I think the idea is just you keep passing it, but eventually what happens to the potato? It cools down, right? That heat is lost when the energy dissipates, right? So that's what's happening here. We're playing hot potato with the electrons whose energy is increasingly lost. Okay? Perhaps it does. So where did the energy go is the question, because the whole point was to use the energy. All right, so here's what we got to remember what we said about redox reactions. And we use methane as an example to illustrate this. Sometimes when redox reactions transfer electrons, they also transfer what we said. They transfer hydrogens, right? But that's what the electron is part of the hydrogen. What else is part of the hydrogen? Protons. Okay. So remember that some redox reactions, including the ones that NAD is involved in, right, involve a transfer of protons as well. That also applies to the redox of the electron transport chain. They're transporting electrons, but they're also transporting protons. Big concept here. As electrons pass down the chain, protons also move. However, not like the electrons. Electrons pass through the chain. Protons pass where?
In the membrane.
Across the inner membrane. Yeah. Electrons pass through the membrane, right? Within the membrane, better way to say it. Within the membrane. But protons move across. Electrons like that, protons like that, electrons like that, protons like that. Okay, so that's a difference. And that was shown across the membrane. Okay? Yeah. So the artist has gone to lengths to show this, right? So you have the differently colored arrows, which I guess red for protons for some reason. But you also see, so where are the protons coming from? The matrix. Where are they going to? The intermembrane space, right. So the artist has shaded the intermembrane space more darkly, so you recognize there's an abundance of protons here. They're all over there. They really should have put in more protons. That would have been maybe one-upping the figure. But this shading here is meant to suggest a concentration of protons. The shading here is meant to show a deficit of electrons, a scarcity of electrons. Excuse me, did I say electrons? Protons, my bad. Abundance of protons, a scarcity of protons. Does that make sense? All right, so hopefully the figures work for you. So what is the chain ultimately doing then? Moving protons, moving protons, moving protons, unidirectionally. It's creating a what? An ion gradient. Yeah. Even more specifically, a proton gradient. You got it. You got it. Okay, this is important because we've said some things about ion gradients and their value in biological systems. All right, so before we say that, okay, yes, this is creating a proton gradient. And what does that action entail? Is this exergonic or is that endergonic? What the chain is doing? It's going to release energy as you do that? Yeah? Okay, let me ask, we need an analogy. If you roll a boulder up a hill, is that exergonic or is that endergonic? Oh, big time endergonic. Good luck. Hopefully, your body's there, right? Because that's a lot of work. If you put water behind a dam, okay, I don't know how that would, but let's say you could gather all the water and put it behind the dam. Is doing that exergonic or endergonic? It's endergonic. That's work. It takes work to move the water. Is that exergonic or endergonic? Endergonic, yes. Yes, we're creating a proton gradient. This action is endergonic. So where did the energy come from? The transfer of the electrons. Right, the electrons. The electrons. The electrons are everything here, folks. The electrons have the energy. They provide the energy to move the protons. Okay? Folks, this is just the first law. One more time. All right, you know, you have objects, in your life that will transform electrical energy into light energy, right? Electrical energy into mechanical energy, electrical energy into even potential energy if you have a battery charger, right? Absolutely. Electron energy into proton gradient energy. First law. Where does the energy come from, everybody? The electron. Yes, yes. We just transformed it one more time. Okay, so let's add this to our concept. So the chain is using the energy of the electrons to transfer protons across the inner membrane, creating a what? Proton gradient. Yeah. Right, so what I like to say is the electron transport chain is sort of got a funny name, right? It's really a misnomer, I think, because the name makes you think the purpose is to transport electrons. Right? Oh, I guess it's about transporting electrons. No! But proton gradient creating chain is not something that flows off the tongue, but that's exactly what its purpose is. That's what it's doing, is creating a proton gradient. Okay? Alright, so to what end? What's the gradient for, everybody? Okay, no terminology that I was talking about. Of course we gotta turn the rotor. We said this. So the proton gradient is used to turn that rotor, making ATP by the enzyme ATP synthase. Right. Proton gradient is used to make ATP by ATP synthase. And one more part of the figure I did not show you is, of course, the enzyme ATP synthase. Because everybody is present in the enzyme, he said, or is present in the membrane, excuse me. Right? There it is. There it is. Now, understand why that happens. This is a proton gradient. Right? More than anything in life, these protons in their intermembrane space want to be where?
Inside.
Yeah. Okay, guys, you gotta work the analogies now, right? So the water behind the dam, more than anything in life, wants to be where?
Outside.
It wants to break the dam. It wants to go forth into the world, but the dam is keeping it back. Same story here, guys. Okay, same story here, right? The protons, more than anything, want to come back to the matrix where they came from. Can they do that? Good luck. No? No? Why can't they come? Why can't they come back? Because they're what? They're charged. Yeah, absolutely. They're charged. And the membrane has a hydrophobic core. This is a barrier to charged solutes. No way they're coming back. Unless they have a transport protein. And ATP synthase certainly is an enzyme, but it's also a transport protein. This transport protein transports what? Protons, hydrogen ions. Yeah, that's what's happening here. So this proton has found a way back into the matrix. It's going to go through ATP synthase. But when it does, there's a release of energy, just like when water flows past the dam, and the water does what? It turns the water wheel. Right? What does the proton do? Turns the rotor, creating conformational change, which makes ATP. Okay? A little bit less impressive. My pointer was on my mouse and so. Okay, anyway, it took some time to put that in there. So this is another example of coupling, by the way, right? So we're coupling, the enzyme is coupling the exergonic flow of protons with the endergonic synthesis of ATP. Let's say that again. So remember, enzymes do coupling, right? So the enzyme is coupling the exergonic flow of protons with the endergonic synthesis of ATP. All right? Questions? Yeah.
So the charge difference between the intermembrane and the intermembrane spaces must be extraordinary.
Yeah, so the question is, what about the difference in charge? So you brought up a great point. The proton gradient is not merely a gradient of solute, but a gradient of charge, right? Because the protons themselves are charged, there's more positive charge here than here. We haven't really talked about this concept of separating charge for the sake of simplicity, but that's a critical aspect. So it's really an electrochemical gradient, right? It's both charge as well as concentration. Good. Cool. All right, there is terminology. In fairness, it was just a little bit early. So remember that we are using a proton gradient to make ATP. The name for that is chemiosmosis. The name that tells you that is chemiosmosis. Chemi for the chemical reaction, making ATP. Osmosis just means move. So movement, we're using movement to make ATP. So the figure, the figure, did it again. The figure is showing that there. So this part here is chemiosmosis. But as you know, another name for this is oxidative phosphorylation. But that is everything that's happening, right? So we're phosphorylating ADP, right? We're phosphorylating ADP. And these are the reactants. These are the reactants, ADP and inorganic phosphate. So using ADP and inorganic phosphate to make ATP, using the power of an electron transport chain, using the redox of the electron transport chain. All of that together is what the term oxidative phosphorylation is telling you, okay? So this is chemiosmosis, but if you add that part, then that's all oxidative phosphorylation. They included that there as well. So this is a great figure, I think. It's not perfect, but it's really good. A lot of information. Yeah.
So just to clarify, oxidative phosphorylation comprises of the electron transport chain and chemiosmosis.
Yeah, chemiosmosis plus the action of the chain. Yeah, that's what that term means. So if you say that term, you're describing that whole process. Okay? Good. So what happens to the electrons? This is an important question, right? Because we haven't said it and because it's consequential. So the electrons were with NADH, and then the first chain, the second chain, the third chain, protein, right? We ended up here with the last chain protein. And that's a problem. Because if the last chain protein has electrons, then the previous chain protein has no one to give its electrons to, right? So if you're holding a potato and someone else has a potato, they can't give it to you. You've already got a potato, right? You've got to get rid of the potato before you can receive one. And if this chain protein cannot get rid of its electrons, then neither can this. So the chain would effectively back up with electrons unless we can get rid of them. What's the solution? Where do you get rid of the electrons?
Water.
Okay, so both true. The answer is oxygen, right? Or green. So how often do you do that? It's because oxygen is the terminal electron acceptor, right? It's the final oxidizing agent of this process. And you need this process because you need ATP all the time. I mean, how long can you hold your breath? That's how much you need ATP all the time. So the chain is oxidized by oxygen. Here it is, and not only will it pick up electrons from the chain, it's also going to pick up protons from solution, and then correct, you get water. So the electrons end up within water in that way. Okay, right there. So here's the reaction. We said one NADH carries 2 electrons. That would combine with 2 protons to make 2 hydrogen atoms, and I guess 1 oxygen would be half an O2, right? And so half an O2, and that would give you 1 water. But what is half an O2? That is molecular oxygen that we are breathing in, right? Not oxygen atoms. So really more accurate to what is happening is this equation, which says 2 NADH provide 4 electrons, combined with 4 protons, an oxygen molecule to make 2 other molecules, right? Just a little more true to life. Okay? All right. So in conclusion, now, here's respiration again for reference. We have now consumed all the reactants, right? We catabolize glucose after stage 3. We use the oxygen in stage 4, right? We've generated both byproducts, right? We made CO2 in pyruvate oxidation in the citric acid cycle. We made water at the end of the electron transport chain. We made both of those now, and we've made ATP. We made 4 ATP for glucose, we said. We have not said how much ATP we made by oxidative phosphorylation. I guess we gotta do that next. The electrons are at an energy minimum. Yeah, please understand, water does not have energy. I mean, unless it's dammed, right? Or unless it's flowing, unless you throw it at someone, water balloon, right? Water does, chemically speaking, water doesn't have energy, okay? Right? So the electrons in water are energy poor.
Excuse me, do you
Yeah.
think you could go back for just 1 second?
Here?
Yes.
Yeah, sure.
Yeah.
Yeah, water has no energy by itself, meaning chemically speaking. Okay? That clear? Okay. If so, let's calculate the ATP, right? Because how much did we make in that last stage? So let's go back. How much did we make in glycolysis? Again, 4, but net production of 2. Okay, very good. How many did we produce in the citric acid cycle? Again, for glucose. 2, also 2 there, right? And that was the 4 we just alluded to, right? Everything per 1 glucose molecule. How many do we make by oxidative phosphorylation? I'm just going to follow what your textbook says, okay, just to be consistent. And there's different ways to tabulate it depending on what all you account for. Long story short, you could either come up with 26 or 28. I think the textbook actually gives you both of those values, right? So, bless you. Yeah, it's a lot more. It's a lot more than you get from these first 2 stages, or prior 2 stages. Okay, so in total, I guess it's either 2 plus 2 plus 26, which is 30, or 2 plus 2 plus 28, which is 32. Either 30 or 32. Okay? Per glucose. And a good question to ask then is how efficient is this? I mean, it looks, I'm saying it in a way that sounds impressive, I guess, but is it really impressive? You can calculate this relatively easily. We said that a mole of ATP will provide 7.3 kilocalories, right? That's what we said. And then we just said that for a mole of glucose, you're making 32 moles of ATP, right? So your ATPs will cancel out, you'll have energy for glucose, but then what did we say about glucose's energy? Well, we said that a mole rather, contains 686 kilocalories. Okay? So we divide the two, all of the units cancel out, you have to multiply by 100 to make this a percentile value. 32 comes out to 32%. Is that efficient?
Pretty efficient.
Hey, there's a second law of thermodynamics we have to consider, right? So we always lose some energy as heat, and so we're losing 68%. We're losing a lot, right? But we're also preserving 32%. That's good. How efficient is an automobile engine? Internal combustion. 20%, I think, right? About 20%, a little bit more maybe? Yeah, so this is good. This is what evolution has brought us to. Pretty good. Question? All right, so not to overstate it, but we've seen the first law of thermodynamics now again and again and again. First, the energy was in the form of glucose, one form of chemical energy. Glucose was oxidized repeatedly, and then we got NADH, it's another form of chemical energy. NADH passed its electrons to the electron transport chain, which created a proton gradient. So this is the point where it really is no longer chemical energy so much as gradient energy, right? Ion gradient, to be exact. And that energy was used to change it back to chemical energy in the form of ATP. Okay, so first law again and again and again and again. Now, that said, what if oxygen is not available? What if that's hypothetically, what if oxygen is just not there? Could this work? Oh, oxygen is the indispensable oxidizing agent, right? So this is the segue now to fermentation, which addresses exactly that. So, if there's no oxygen, the last chain protein has nowhere to ditch the electrons. You can't ditch the electrons. And then if that guy is stuck with the potato, then so is that, and so is that, and so is that, and so is that. So the chain backs up with electrons. And if you go back far enough, you get to what? Because let's take it all the way. What about NADH? If the chain is full of electrons, what about NADH? What about its electrons? So there's a couple of consequences here. One, the chain filled with electrons stops functioning. It depends upon its ability to ditch the electrons. If there's no oxygen, you also have nowhere for NADH to give its electrons to, right? If the chain is full of electrons, NADH can't give its electrons to anyone. Another way to say that is NADH has no oxidizing agent. Very good, right? Exactly. And that's important because how do you get back to NAD? Remember, you have a cyclical relationship between NAD, NADH, NAD, NADH. If it's all NADH, you have no NAD, which all stages 1, 2, and 3 need. All those stages need NAD. Okay, let's consider. If you have no oxygen, then the electron transport chain has nowhere to give its electrons to, right? So you're back here. If the chain is full of electrons, NADH has nowhere to give its electrons to. So now you're here. You can't get back here. And if you have no NAD, then you can't do this. So this is stage 1, stage 2, and stage 3. You can't do that, right? So again, with no oxygen, you have no electron transport chain at your disposal, and then you have no NAD and no way to do anything at that point. So NAD is going to go through the floor, right? NAD levels drop, and then everything breaks down, unless we find a solution. What is the solution?
Non-organic.
It was something we call fermentation. So here's what we do. We're not going to do the entire catabolism. We'll do an incomplete catabolism. Okay, so an incomplete catabolism without oxygen. And how incomplete is that? Well, we'll just do glycolysis. Okay, we won't go even beyond glycolysis. We'll just do glycolysis, which, does glycolysis make ATP?
Yes.
Yeah, it does. Okay, so we could get a little ATP from glycolysis alone. But it still doesn't answer how do we get NAD, because glycolysis also has an oxidation in it, right? We've got to get NAD. So how do we get NAD? What does glycolysis end with? We split sugar and we get to pyruvate, right? So we'll just use pyruvate as the oxidizing agent. That's it. So we use pyruvate as the oxidizing agent. So NADH gets oxidized by pyruvate, getting us back to NAD. That's the whole answer. Let's take a look. So this is glycolysis, right? You go from glucose to pyruvate. Again, you'll make ATP 2 per glucose, but you also have an oxidation, and so you're stuck with NADH if the chain is not functioning. So we oxidize NADH using pyruvate. thereby recycling the NAD and keeping glycolysis running, keeping glycolysis running, keeping that ATP a little bit anyway being made. Okay, so that will give us another product because you're now reducing pyruvate, right? So that is, in this case, that's called lactic acid. And so for this reason, what I showed you here is lactic acid fermentation. Produces lactic acid. Lactic acid fermentation, it's called. Okay? As opposed to what? Well, there's variations here in how this can be done. But let's stick with this for the moment. Be aware that some bacteria can do lactic acid fermentation when oxygen is limiting, but so can you. So can mammals do lactic acid fermentation under some conditions. Where in your body do you do lactic acid fermentation?
Muscles.
In the muscles, yeah. Yeah, when you make an extreme demand for energy, right? So remember, muscle contraction depends on ATP energy. This is all ATP hydrolysis doing that, okay? So when you go to do a bench press, right, and really load it up, when you go to do that, when you go, to do your sprint, against your best buddies, see who can, when you wrestle, arm wrestle, that's a big demand for energy. At that point, you can't bring in oxygen into your lungs, into your blood, to all the cells of your body quickly enough. The oxygen is not getting there quickly enough to meet the demand for ATP. Okay, so at that time, you can switch. It doesn't mean you stop breathing, right? But maybe for a moment, and get a little bit more ATP from doing that. Right? This gets you through that thing. We'll get you through. How long can you do that? Right? Not so long, but it gets you that little bit more effort. Okay? Another way to do this is to first convert pyruvate to another chemical here. I won't tell you the name, but this chemical, in turn, pyruvate derivative, could be used to oxidize NADH, again back to NAD. Now that produces yet another chemical called ethanol. And so for that reason, this is known as alcohol fermentation. Some bacteria do that. Who else does that? Yeah, brewing yeast, right? Brewer's yeast does that. That happens during the brewing of alcoholic beverages. Also happens during baking. It's the same yeast, right? Saccharomyces cerevisiae. Yeah. Another variation of fermentation. Questions? Okay, so different ways of making ATP. I have a question then. What did we say bacteria do? Do they do fermentation or do they do respiration?
Both.
Oh my gosh, both. Yeah. Okay, so I didn't want to confuse you there, and so I thought we should say that, right? So please understand where we got respiration from, right? Remember mitochondria, once upon a time were bacteria, okay? So absolutely, even single cell life, bacteria, yeast can do respiration. They prefer it, but they can also switch to fermentation under certain circumstances. I mean, like we can also do fermentation when the need arises. Okay? What about fish? Do fish do respiration? They live underwater. There's no oxygen there, is there? Of course there is. Water goes into the oxygen goes into the water, and fish can do respiration. Okay, so remember, respiration is the best way to make ATP. Almost everybody does it. Okay? All right. So what fuels respiration? I told you the tradition is to talk about sugar, right? Glucose. But actually, we know that there are three energy nutrients, right? So let's specify now that all of these can serve as energy sources for respiration, carbs, fats, and proteins. Now, we said back in chapter 5, we consume starch, we consume disaccharides, sucrose, maltose, and lactose, and fruit contains fructose. Okay? So, what happens when we consume those? Well, starch is made of what? Alpha glucose, right? So that's broken down to glucose, which enters at stage 1 of glycolysis. Remember that all the disaccharides contain at least one glucose, and when you break a disaccharide into the two monosaccharides, then the glucose can enter glycolysis, right? But then you have these other monosaccharides that these are made from. You also have fructose here. So I guess the question is, what about other monosaccharides? So glucose we've established can fuel respiration. What about other monosaccharides? Good question. Let's address that in this figure. Okay, so this figure from your text shows all the stages of respiration. Very simple scheme, right? Glycolysis, pyruvate oxidation, citric acid cycle, and oxidative phosphorylation. Okay, so what did we just say? Well, carbs are broken down into glucose, which again, stage 1, step 1 in fact, of stage 1. Okay, but understand that other monosaccharides, like fructose, are going to merely work in at other steps. Okay, go back and look at some of the names of the various products made during glycolysis. And I didn't mention them because I didn't want you to worry about knowing them. But look at the names and you'll see a lot of them seem like some of the other monosaccharides we talked about. Fructose, galactose. So all the monosaccharides can work into glycolysis. If it's not step 1, it's maybe a later step. But once you're in, everything that happens afterward is the same. Okay, once you've entered the stages of metabolism, everything else is the same. Okay? So let's deal with fat. Fat consists of what? Okay, they could be saturated or unsaturated, but what are they made from? Glycerol, good, and fatty acids. Okay, so glycerol, remember, is basically a monosaccharide, right? Once again, look at the names of the intermediates of glycolysis and tell me you don't see a name that looks like glycerol in there, okay? So fats, yes, there it is, are going to break down into glycerol, which can enter at a later step of glycolysis. Fatty acids, nothing like sugar, okay? So they will not do glycolysis, but they will break down into 2 carbon units because the fatty acid, the hydrocarbon chain. They'll break into 2 carbon units which get picked up by coenzyme A, right? So you get acetyl coenzyme A. So they're going to be converted to acetyl coenzyme A, and at that point you just go through the citric acid cycle. Citric acid cycle made from NADH? Oh my God, most of the NADH is made from the citric acid cycle. So who cares if you skip stages 1 and 2? You've got fats produce tremendous energy, as you know. Last but not least, proteins are made from what? Amino acids, of course, and that's shown way down here. So proteins are broken down into amino acids, most of which can enter respiration as some step of the citric acid cycle. Okay, so later steps, earlier steps, and once you're in the cycle, again, you have tremendous potential for oxidation. I think there's some that can even enter here as glycolytic intermediates. Okay? Right, so the point is that all of our energy nutrients will undergo respiration to make ATP. if you look really closely at these arrows, some of them are coming in, but some of them are going out. So please recognize that now. Some arrows coming out. What are they about? That is merely to nod to, you don't have to use the energy nutrients all the way and make ATP. You don't have to use them for energy. You could rather use them as a building material. Right? So remember, we said carbs and fats and protein are energy sources, but they're also a source of carbon. You simply redirect from metabolism into anabolic pathways. Yeah, so the arrows coming out are redirecting nutrients to anabolic pathways. And I actually have a figure to show this right here.
What?
Huh? Do you recognize anything here?
No.
Really? No? Yeah, the citric acid. I mean, let's go up here. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, we got glycolysis. And we have a citric acid cycle. You can see that. Okay, so that's respiration. But understand the potential. You can go through that, or you can redirect into all of this potential anabolism. Okay, so here's the anabolism that you could do alternatively. Okay? So again, nutrients we consume can be used for either purpose. Yeah, and we'll talk about anabolism in the last couple of chapters of the course. So don't forget, don't forget that drill. All right, last but not least, folks. Okay, she's done, but that's okay. So we ended chapter 8 by saying that enzymes could be controlled, remember? And because enzymes could be controlled, entire pathways could be controlled. We talked about how isoleucine manufacture is controlled through one enzyme, right? If you shut off that enzyme with isoleucine, when it builds up, then you stop doing that step, which shuts every step down. You no longer make isoleucine. Until you use up the isoleucine, you stop doing that, the enzyme is back on, and then it cranks up again, right? So is there such regulation within respiration? Are you just going to make ATP anytime, even when you have enough of it? Of course, you stop when you don't need ATP, right? So respiration is actually regulated through an enzyme of glycolysis. Right? Go back to the first thing. An enzyme of glycolysis, we would call it PFK. What is PFK? It's the third step. Close enough, right? The third step of glycolysis. And like the enzyme from isoleucine biosynthesis, this enzyme has allosteric sites. And interestingly, it can actually be turned off, but it could also even be turned on. Okay, I'm going to say something about both of those things. All right, and again, this is going to be an example of feedback inhibition. So here's the enzyme, PFK, and while it does have several catalytic sites, it also has several allosteric sites, which allow it to be turned off and on. For example, ATP, when it builds up, will bind to PFK. The arrow down here means turning off PFK. Of course, ATP turns off PFK. Now, interestingly, when you use ATP, what do you get? What is it? When you break down ATP, what do you get?
ADP.
Energy, also ADP, right? So you use ATP, you get ADP. Use more ATP, you get ADP. It turns out ADP, and actually AMP as well, are signals to the cell, we need ATP. Okay, there's so much ADP now, we need ATP, So when these chemicals bind to PFK, they will actually, up arrow, turn it on. They will turn it on. One more. Citric acid, which you remember is the first product of the citric acid cycle, will bind to PFK and turn it off. Just like ATP turns it off, it shuts it off as well. All right. Glycolysis, PFK. All right. And everything else. When ATP builds up, it binds to PFK, turning it off. Okay? And then you don't do glycolysis, you don't do anything else, you don't make ATP. Alternatively, we said ADP and AMP bind PFK, turn it on, because when you make a lot of those, it means the cell needs ATP. Last but not least, citric acid from citric acid cycle binds, turns it off. Now, why is that the case? If you have a boat of citric acid, do you need to do glycolysis right now?
No.
No, you have the first product of the citric acid cycle, you can crank the cycle. You can keep going. You can do tons of NADH without doing any of that. So that's a way to synchronize glycolysis in the citric acid cycle. There's no reason to do glycolysis. Question?